Okay, looking further into what we have regarding reducible second order differential equations. And now you're going to have some of the equations to be homogeneous and non-homogeneous, where you could potentially use the method of undetermined coefficients, or take what we have with the characteristic root equation, but just utilizing the techniques in case you cannot use either of the aforementioned techniques. And let's say that for these reducible equations that have the dependent variable y missing, and let's say, just as an example, so we have y double prime plus 2 minus 8x is equal to 0. And if I isolate the second order derivative of y with respect to x, I'm going to have y double prime is equal to 8x minus 2. Now for y double prime, if I put this in terms of the substitution variable p, now it is when the variable y is missing that if we have the substitution variable p to appear, well, y double prime is going to be dp over dx. Now again, the first order derivative of y with respect to x, that would be just p. But for y double prime, we have dp over dx. And dp over dx we have equal to 8x minus 2. And separating the differentials and solving in terms of the substitution variable p, we have that p is equal to 4x squared minus 2x plus a constant. And again, for p itself, that is going to be in reference to y prime or dy over dx. So looking at solving for y, okay, we have dy over dx equal to 4x squared minus 2x plus the constant. And separating the differentials, okay, and taking the antiderivative, we have for our solution in y, we have that equal to 4/3 of x cubed minus x squared plus the first constant times x plus another constant. So this is a case of where we have in the appearance, we had the variable y to be missing. And if we take as another case, and say that we have y double prime plus 1 over x y prime is equal to 3. Now this is a case of where we have to utilize the substitution variable p. And again, whenever y is missing, again, y prime is going to be at p. And 1 over x y prime, that will translate to 1 over x times p, or p over x. Again, y double prime, we have it dp over dx. And the sum of dp over dx and p over x is equal to 3. And we have, in this particular case, all right, we have the equation to be linear in the substitution variable that we have in p. Okay, so we have setting things up for the integrating factor. Now you have this p of x, and that's not the same as the substitution variable p. This is like your algorithmic p, like in the first order linear differential equations. And we have that p of x is equal to 1 over x, and we have q of x is equal to 3. And for the integrating factor, we have e to the integral of 1 over x dx, which is going to be e to the natural logarithm of x, which becomes x. And multiplying what we have in the standard form of b interacting with x, we have x times the quantity of dp over dx plus p over x is equal to 3 times x. And looking at what we have on the left-hand side, if I were to have distributed, this would have been the product rule expansion of taking the derivative in x of multiplying the integrating factor x by the substitution dependent variable p. And that is equal to 3x. And shifting over and freeing up xp from the parentheses, and I'm going to integrate 3x dx, and integrating over 3x dx, we're going to have in the next line, we have x times p is equal to 3/2 of x squared followed by a constant. And then looking at isolating p, we have with division by x, we had that p is equal to 3/2 of x plus the constant divided by x. And looking at solving ultimately for y, again, by definition, okay, p is the substitution for dy over dx. and setting this equal to 3 halves of x plus the constant over x. And if I separate the differentials, so you have dy is equal to 3 halves of x plus the constant c sub 1 over x, and integrating over both sides. So we're going to have that y is equal to 3/4 of x squared plus c sub 1 times the natural log of x, followed by the addition of a second constant. Okay, now a case of a second order differential equation that is reducible, but we cannot utilize the method of undetermined coefficients. Here we had the second order derivative of y with respect to x is equal to the square of 3 times the derivative of y with respect to x. And just by substituting, now y double prime, we have a dp over dx if we consider that we had the variable y to be missing. And we have that set equal to the square of 3 times p, again where p is in reference to the first order derivative of y with respect to x. And for what we have in this case, so squaring out 3p, we have dp over dx is equal to 9p squared. And looking at separating the variables, so if I simultaneously divide by p squared and multiply by dx, so we have dp over p squared is equal to 9dx. And looking at integrating over both sides, so we have negative 1 over p is equal to 9x plus the first constant. And if I change the sign at both ends, we can say that we have 1 over p is equal to negative 9x. And we'll just say we have plus c sub 1. You could say plus alpha. And now just flipping what we have here, or considering that what we have with 1 over p. Okay, now p is going to be dy over dx. And for the reciprocal of p, we have dx over dy is equal to negative 9x plus c sub 1. And if I separate the differentials and variables, we can say we have dx over negative 9x plus c sub 1 is equal to dy, and then just rearranging the terms, so we have dy is equal to dx over negative 9x plus c sub 1, and integrating over both sides. So we're going to have that y is equal to negative 1/9 of the natural logarithm of negative 9x plus c sub 1 plus c sub 2, and you can also write this as y is equal to the natural logarithm of the quantity of negative 9x plus c sub 1 raised to the negative 1/9 plus c sub 2. Okay, another equation where we have the independent variable x missing, and I just want to do a little bit of revisiting of the use of the method of undetermined coefficients, and then we'll get to the p substitution in a moment. But again, say we have y double prime minus 8 is equal to 0, and we have that y double prime is equal to 8. And if I were to use a characteristic root equation to determine the complementary solution of this equation, you would have like y double prime is equal to 0, and putting in characteristic root terms, y double prime translates to r squared is equal to 0. And what's going to happen here is that with r to the second power, there is only one root with 0, and that is going to repeat once. So the complementary solution we're going to have equal to the constant c sub 1 plus another constant times x with c sub 2 times x. Now for 8, if we were to set things up along the lines of establishing the use of the family of derivatives, again, 8 is a constant. And notice that I have underlined the c sub 1 from the complementary solution and the constant from the family. And here we have a duplication with c of c sub 1. And I can try to remove duplication upon multiplying what is in the family by x. So a constant times x is going to be an x term. Well, guess what? We have from the complementary, we have the x, a constant times x. Well, guess what? We have another duplication. So I'm going to have to multiply by x once more. So I had to remove duplication twice. And so we have x squared as the resulting family derivative term. And there's no x squared expression in the complementary solution. So I can set things up in the particular where I have y sub p is equal to ax squared. And I'm going to be going out to the second order derivative. Now the first order derivative of y sub p is going to be 2ax, and the second order we have with 2a, and putting the original equation in terms of the particular. So we have y sub p double prime minus 8 is equal to 0, and with substitution we have 2a minus 8 is equal to 0, and from this we're going to have that a is equal to 4, and putting back in the particular. So with a at 4, okay, we have y sub p is equal to 4x squared. And for the overall solution, we're going to have that y of x is equal to 4x squared plus c sub 1 plus c sub 2 times x. Now, crossing over to what we have in the substitution pattern. Okay, now you could treat this as either an equation where the variable x or y is missing. But let's say that in the case of where x is missing. Okay, so for y double prime, you have p dp over dy minus 8 is equal to 0. And if I isolate p dp over dy, okay, we have that equal to 8. And then separating the variables. In this case, we're going to be looking at multiplying both sides of the equation by dy. So we have p dp is equal to 8 dy. And integrating over both sides, so we have p squared over 2 is equal to 8y plus a constant. And if I multiply by 2, so we come out to p squared is equal to 16y, and we can say that alpha will represent 2 times that first constant. And looking at expressing for p, we're just going to take the positive square root of 16y plus alpha. Now, if we treat this equation, again, as where the variable x is, or in this case, yeah, where the variable x is missing, and we're going to have 4p. Okay, so we have dy over dx is equal to the square root of 16y plus alpha, and looking at separating the variables. So we're going to have dy over the square root of 16y plus alpha is equal to dx, and integrating. Now the easy part is with dx, so you're going to have x plus yet another constant. And for dy over the square root of 16y plus alpha, you have with the method of substitution and the power property. Okay, so if I set u equal to 16y plus alpha, and we have dy to be du over 16, and we have for the reciprocal of the square root of u, antiderivative will be 2 times its square root. So we have 1/16 times 2, which is going to be 1/8, and we have times the square root of 16y plus alpha, and you have, of course, followed by the constant. Okay, so I'm just going to add that in. And looking at going back to our equation. So filling in, we have 1/8 of the square root of 16y plus alpha is equal to x plus a second constant. And if I multiply both sides of the equation by 8, so we have the square root of 16y plus alpha is equal to 8x, and we'll say that we have beta for 8 times c2, or c sub 2. And squaring both sides, we're going to have 16y plus alpha is equal to the square of the quantity of 8x plus beta. And we have for 16y, we had the square of 8x plus beta minus alpha. And isolating y, we have y is equal to the square of the quantity of 8x plus beta minus alpha over 16. And let's say that if I were to expand this expression on out, and if you notice, okay, we have y is equal to 64x squared plus 16 beta x plus beta squared followed by the subtraction of alpha. And we'll take that difference of the constants, where you have the difference of constants is still going to be a constant, so I'm just going to refer to this as gamma. And we have this whole expression over 16, and in reduced terms, so we're going to have 4x squared plus beta x, and we'll say we have for delta, where delta represents gamma over 16, and that is going to be the solution that we have with the substitution. And notice how this is going to compare with what we had with the method of undetermined coefficients. So we still had the 4x squares, and we say that beta x is like the equivalent of c sub 2x, and the delta we have as the equivalent of what we otherwise had as the first constant in the use of the method of undetermined coefficients. Okay, now shifting gears, let's say if we look at solving problems where we have treating as an equation where we have the missing variable to be the independent variable x. And just looking at what we had dealt with a moment ago with y double prime equal to the square of 3y prime. And we had treated this where we had the variable y to be missing. But let's say that if we had x be missing. Now, for y double prime, when y was treated as being the missing variable, we had y prime to be, in this case, we had dp over dy. But if we treat x as missing, well, instead of dp over dy, we will have p dp over dy. And we still have 3y prime squared is going to be 3p squared. Notice throughout, okay, in the equation, you don't have the letter x or the letter y missing. But if we treat x as the missing variable, just note that the difference with x missing, y double prime we treat as p dp over dy, not just dp over dy, as was the case with the missing y. So squaring the right-hand side of the equation, so we have once again 9p squared, and so now we have p dp over dy is equal to 9p squared. And if we simultaneously divide by p squared and multiply by dy to separate the variables, notice we have p divided by p squared is going to be the reciprocal of p. Dp is equal to 9 dy, and integrating over both sides. So we're going to have the natural logarithm of p is equal to 9y plus a constant. And taking care of the natural logarithm on the left-hand side. So if I take both sides and treat as powers to which the natural logarithmic base e is going to be raised, well, e to the natural logarithm of p is going to be p. And for the activity to the right, we can say that is going to be translated to a constant, and we'll say alpha times e to the 9y. So we have p is equal to alpha times e to the 9y. And again, we have p, whether the variable missing is x or y, p is still going to be at dy over dx. And so we have dy over dx is equal to alpha times e raised to the 9y. And separating the variables. Okay, so we have dividing by e to the 9y and also multiplying by dx. So we have dy all over e to the 9y is equal to alpha dx, and integrating over both sides. So we have the integral of the reciprocal of e to the 9y dy, or the integral of e to the negative 9y dy. That is going to be negative 1/9 of e to the negative 9y. And to the right, I have alpha x plus a second constant. Multiplying by negative 9, we have e to the negative 9y is equal to, we can say, beta x plus gamma. And taking the natural logarithm of both sides, we have the natural logarithm of e to the negative 9y is equal to the natural logarithm of the quantity of beta x plus gamma. So we have negative 9y is equal to the natural logarithm of beta x plus gamma. And we have, with division by negative 9, we're going to have the negative of the natural logarithm of the quantity of beta x plus gamma all over 9. And the appearance of that answer is going to look a little different from what we had in the case of treating the equation as where y was the missing variable. Okay, where we had the solution to be like negative 1/9 of the natural logarithm of negative 9x plus the constant, and then we have followed by another constant. So those are two different ways of saying the same thing, whereas inside we have a constant times x plus another constant, whereas here we had the specified constant inside the parentheses alongside x to be negative 9. The work with beta x plus gamma is going to be worked out to kind of compensate for the adding of the additional constant whenever we treated y as the missing variable.